What specific problem does AGENTSNET aim to solve in the context of multi-agent systems and distributed computing?
AGENTSNET aims to address the gap in evaluating the core competencies of multi-agent systems, specifically focusing on scalable coordination, decentralized communication, and collaborative reasoning. It introduces a principled benchmark that measures these capabilities through 5 fundamental problems from distributed computing: graph coloring, minimal vertex cover, maximal matching, leader election, and consensus. These tasks are designed to assess how well multi-agent systems can self-organize, coordinate, and communicate effectively in various network structures and scales. By grounding its evaluation in distributed systems theory, AGENTSNET provides a comprehensive framework to analyze the performance of LLM-based agents in solving complex reasoning problems collaboratively. Ultimately, AGENTSNET seeks to enhance the understanding of multi-agent coordination and collaboration, which are essential for effective distributed systems.
How does the proposed AGENTSNET framework work? Please illustrate it step by step, detailing the methodology, tasks, and communication protocols involved.
The AGENTSNET framework operates by evaluating multi-agent systems on fundamental distributed computing problems through a structured methodology. First, it identifies 5 core tasks: coloring, VERTEXCOVER, matching, LEADERELECTION, and consensus, each representing a specific coordination and collaboration challenge. Agents are organized in various network topologies, such as small world, scale-free, and Delaunay graphs, to simulate real-world interactions. Communication occurs via a message-passing protocol inspired by the local model, where agents exchange messages with their immediate neighbors in synchronous rounds, allowing them to base decisions on local information. After a predetermined number of message-passing rounds, agents provide their final responses, which are evaluated based on strict criteria to determine the success of their coordination efforts.
Can you provide a simple example of how one of the tasks in AGENTSNET, such as the leader election, operates in practice? Walk through the main steps with a hypothetical scenario.
In the leader election task of AGENTSNET, the goal is for a network of agents to select a single leader among themselves. The process begins with each agent being prompted to identify whether it believes it is the leader, after a series of message-passing rounds. For instance, consider a network of 4 agents, A, B, C, and D. Initially, each agent may have a unique identifier or priority level. During the first round, agents exchange messages with their neighbors, sharing their identifiers. After a few rounds of communication, agents compare their identifiers and decide to acknowledge the agent with the highest identifier as the leader. If agent A has the highest identifier, it will announce yes to indicate it is the leader, while the others will respond no. The task is successfully completed when all agents confirm that only one agent, A, is designated as the leader, demonstrating effective coordination and communication among the agents.
What are the theoretical or practical advantages of using AGENTSNET over existing benchmarks in evaluating multi-agent systems?
AGENTSNET offers several theoretical and practical advantages over existing benchmarks for evaluating multi-agent systems. Firstly, it is grounded in distributed systems theory, focusing on core competencies such as scalable coordination, decentralized communication, and collaborative reasoning, which are often overlooked in other benchmarks. Secondly, AGENTSNET incorporates 5 fundamental distributed computing problems: graph coloring, minimal vertex cover, maximal matching, leader election, and consensus, allowing for a comprehensive assessment of agents' self-organization and communication capabilities across diverse network structures. Additionally, it supports a practically unlimited number of agents, scaling experiments up to 100 agents, which is a significant improvement over existing benchmarks that typically evaluate smaller agent networks. Finally, AGENTSNET employs a robust message-passing protocol that reflects real-world communication dynamics, enhancing the relevance of its evaluation metrics compared to traditional benchmarks.
How is AGENTSNET validated or tested? What metrics or datasets were used to demonstrate its effectiveness in assessing multi-agent coordination and collaboration?
AGENTSNET is validated through a series of benchmarking tasks derived from fundamental problems in distributed computing, specifically focusing on tasks like coloring, VERTXCOVER, matching, LEADERELECTION, and consensus. The effectiveness of AGENTSNET in assessing multi-agent coordination and collaboration is demonstrated using a binary evaluation metric, which counts only fully correct solutions where the entire agent network satisfies the task specifications. Additionally, the benchmark employs a diverse set of 27 network topologies, including small world, scale-free, and Delaunay graphs, with sizes ranging from 4 to 16 nodes, to evaluate the agent's performance across different scenarios. The results are reported as the fraction of solved instances per task, with standard errors of the mean calculated to provide statistical reliability. Furthermore, qualitative analyses of agent interactions and strategies are conducted to gain insights into the communication and collaborative capabilities of the models tested on AGENTSNET.
What significant results were achieved with AGENTSNET, and how do these results compare to existing benchmarks? What insights can you draw from the performance of different LLMs on AGENTSNET?
AGENTSNET demonstrated significant results by effectively evaluating the coordination and collaboration capabilities of various LLMs across 5 fundamental distributed computing problems: coloring, VERTXCOVER, matching, LEADERELECTION, and consensus. The benchmark revealed that no model consistently excelled across all tasks, with performance generally declining as graph size increased, particularly for the VERTXCOVER task. Notably, the best-performing models were Claude 3, 7 Sonnet, Gemini 2.5 Pro, and Gemini 2.5 Flash, with Gemini 2.5 Flash being more cost-efficient while maintaining competitive performance. In comparison to existing benchmarks, AGENTSNET fills a critical gap by focusing on structured coordination and collaboration, which were previously under-evaluated. Insights from the qualitative analysis indicated that many LLMs struggled with strategy coordination, often leading to late agreement on strategies or failure to communicate effectively, highlighting areas for improvement in multi-agent systems.